In this module, we shall learn about sample correlation and association along with the test of hypothesis. Let us begin by understanding the meaning of correlation and association. In a bivariate distribution, we may be interested to find if there is any relationship between the various under study. The correlation is a statistical tool which studies the relationship between two variables, and correlation analysis involves various methods and techniques used for studying and measuring the extent of relationship between the two variables. The two variables are said to be correlated if the change in one variable results in a corresponding change in the other variable. Sample correlation and association are two ways of explaining a relationship between two statistical variables. Association is a more generalized term and correlation is a special case of association where the relationship between the variables is linear and in nature. The statistical term association is defined as a relationship between two random variables which makes them statistically dependent. It refers to rather a general relationship without specifics of the relationship being mentioned, and it is not necessary to be a causal relationship. Correlation is a measure of the strength of the relationship between two variables. The correlation coefficient quantifies the degree of change of one variable based on the change of the other variable. In statistics, correlation is connected to the concept of dependence, which is the statistical relationship between two variables. One of the statistical methods to study the association between two variables is Pearson's correlation coefficient. The correlation coefficient quantifies the degree of change of one variable based on the change of the other variable. After studying this module, you shall be able to: number 1, understand the concept of correlation coefficient. Number 2, calculate the Pearson product moment correlation coefficient. Number 3, interpret the Pearson product moment correlation coefficient. Number 4, perform the test of hypothesis of population correlation coefficient and identify the limitations of correlation coefficient concept. Let us understand the meaning of correlation coefficient. A correlation coefficient is a coefficient that illustrates a quantitative measure of some type of correlation and dependence, meaning statistical relationship between two or more random variables or observed data values. One of the most important methods for calculating correlation coefficient is Karl Pearson's correlation coefficient. It is a mathematical method for measuring the intensity or the magnitude of linear relationship between two variable series and was suggested by Karl Pearson 1867 to 1936, a great British biometrician and statistician, and is by far the most widely used method in practice. Karl Pearson in 1900 developed Pearson product moment correlation coefficient represented by R, also known as correlation coefficient, to measure the strength of a correlation. The correlation coefficient is a number that gives us the direction and degree, that is closeness, of linear relations between two variables. The correlation coefficient gives us a line of best fit through the data of two variables. The correlation coefficient can take values between -1 to +1. The sign of correlation coefficient, whether it is positive or negative, determines the direction of the relationship between the two variables. If the correlation is positive, that is R is greater than 0, as the value of one variable increases, so does the other. Whereas if the correlation is negative, that is R is less than 0, then the value of one variable decreases as the other variable increases. In other words, the Pearson's correlation coefficient, or just the correlation coefficient R is a value between -1 and 1, that is -1 is less than equal to R is less than equal to +1. It is most commonly used correlation coefficient and valid only for a linear relationship between the variables. If R is equal to 0, no relationship exists, and if R is greater than equal to 0, the relationship is directly proportional. The value of one variable increases with the increase in the other. If R is less than 0, the relationship is inversely proportional. One variable decreases as the other increases. The base formula for calculating correlation coefficient is as follows. R is equal to n sigma xy minus sigma x into sigma y whole upon square root of n into sigma x square minus sigma x whole square multiplied by square root of n sigma y square minus sigma y whole square. In the formula, n represents the number of ordered pairs that are there in a sample. X and y are the two variables, and the square root SQRT stands for the square root. Dividing numerator and denominator by n, we get R is equal to sigma xy minus sigma x sigma y upon n whole upon square root of sigma x square minus sigma x square upon n multiplied by sigma y square minus sigma y whole square upon n. Next, we present the deviation score formula. It gives the average cross product of the standard scores of the two variables, but in a computationally easier format. R is equal to sigma xy upon square root of sigma x square sigma y square. The variables x and y in the formula above have been transformed from the original variables by subtracting their means. Lastly, we present the covariance formula, which is yet another approach. It is defined as the ratio of covariance between x and y to the product of the standard deviation of x and y. R is equal to covariance of x and y upon S of x, S of y, where R is often denoted as Rxy to emphasize the two variables under consideration. This explains the methodology to calculate the Pearson's correlation coefficient. We can illustrate this by a numerical example. Illustration 1. The table gives us the values of x and y. When x is 1, y is 2, x is 3, y is 4, x is 4, y is 5, x is 4, y is 8. The value of two variables x and y is given. We have to compute the correlation coefficient. Sigma xy is equal to 69, sigma x is equal to 12, sigma y is equal to 20, sigma x square is equal to 42, and sigma y square is equal to 118. Applying the formula, we get R is equal to 69 minus 12 into 20 upon 4 whole upon square root of 42 minus 12 square upon 4 multiplied by 118 minus 20 square upon 4, which comes out to be 0.866. Hence, correlation coefficient comes out to be 0.866. Illustration 2. The correlation coefficient between two variables x and y is 0.48. The covariance is 36. The variance of x is 16. Find the standard deviation of y. Using the formula, R is equal to covariance of x and y upon Sx Sy, we get 0.48 is equal to 36 upon 4 into Sy, which implies Sy is equal to 18.75. Hence, the standard deviation of y is 18.75. Moving on to the properties of the correlation coefficient. Karl Pearson's correlation coefficient possesses the following properties. First, limits for correlation coefficient, that is Pearson's correlation coefficient, cannot exceed 1 numerically. In other words, it lies between -1 and +1. Symbolically, -1 is less than equal to r is less than equal to 1. Here r is equal to +1 implies perfect positive correlation between the variables, and r is equal to -1 implies perfect negative correlation between the variables. Second, correlation coefficient is independent of the change in origin and scale. Third, two independent variables are uncorrelated, but the converse is not true. One should not confuse with the words of uncorrelation and independence. Rxy is equal to 0, that is, uncorrelation between the variables x and y simply implies the absence of any linear relationship between them. They may, however, be related in some other form other than the straight line, example, quadratic, logarithmic, or trigonometric form. Further, we have the interpretation of correlation coefficient. The Pearson correlation coefficient R can take a range of values from +1 to -1. A value 0 signifies that the two variables have no association between them. In other words, there is no linear relationship between the variables. However, r equal to 0 does not imply that variables are independent. Positive association is implied by a value greater than 0, which means that as the value of one variable increases, so does the value of the other variable. Negative association is implied by a value less than 0, which means that as the value of one variable increases, the value of the other variable decreases. If r is equal to +1, it implies that there is a perfect positive correlation between the variables. In other words, the scatter diagram will be a straight line starting from left bottom and rising upwards to the right top. If r is equal to -1, there is a perfect negative correlation between the variables. For other values of r lying between -1 and 1, there are no set rules for its interpretation. The maximum we can conclude is that nearer is the value of r to 1, the closer is the relationship between the variables, and nearer is the value of r to 0, the less close is the relationship between them. One should be very careful in interpreting the values of r, as it is often misinterpreted. The stronger the association of the two variables, the closer the Pearson correlation coefficient r to 1 will be either -1 or +1, depending on whether the relationship is positive or negative respectively. Achieving a value of +1 or -1 means that all your data points are included on the line of best fit. There are no data points that show any variation away from this line. Values for r between -1 and +1, for example, r is equal to 0.8 or -0.4, indicate that there is a variation around the line of best fit. The closer the value of r to 0, the greater the variation around the line of best fit. We shall understand correlation coefficient graphically. The figure shows the scatter of the data points around the line of best fit under various cases of different values of correlation coefficient. In the panel, the correlation coefficient shows a positive relation, with value 0.07 indicating high positive correlation and value 0.3 indicating low positive correlation. Value equal to 0 shows no correlation between the variables x and y. In the panel, negative correlation between the variables has been shown. The value of minus 0.7 indicated high negative correlation, whereas value of minus 0.3 shows low negative correlation between the variables. Correlation coefficients whose magnitude is between 0.9 and 1.0 indicate variables which can be considered very highly correlated. Correlation coefficients whose magnitude is between 0.7 and 0.9 indicate variables which can be considered highly correlated. Correlation coefficients whose magnitude is between 0.5 and 0.7 indicate variables which can be considered moderately correlated. Correlation coefficients whose magnitude is between 0.3 and 0.5 indicate variables which have a low correlation. Correlation coefficients whose magnitude is less than 0.3 have little, if any, linear correlation. We previously learned to evaluate whether or not a linear relationship exists between two variables. We can now answer our research question about whether there exists a linear relationship by using the t-test for testing the population correlation coefficient. H naught rho equal to 0. The sample correlation R estimates population correlation rho. Firstly, we specify the null and alternative hypothesis. Null hypothesis H naught rho equal to 0. Alternative hypothesis HA rho is equal to 0 or HA rho less than 0 or HA rho greater than 0. Then we calculate the value of the test statistic by using the formula test statistic T star is equal to R multiplied by under the root n minus 2 whole upon 1 minus R square. We use the resulting test statistic to check the significance using t-table of critical values to make a decision. The other method is used by using p-values. The p-value is determined by referring to a t-distribution with n minus 2 degrees of freedom. If the p-value is smaller than the significance level alpha, we reject the null hypothesis in favor of the alternative. We conclude there is a sufficient evidence at the alpha level, conclude that there is a linear relationship in the population between the predictor X and the response Y. If the p-value is greater than the given significance level alpha, then we fail to reject the null hypothesis. We can thus infer that there does not exist enough evidence at the alpha level to conclude that there is a relationship in the population between the predictor X and response Y. We can explain the concept by using an example. Illustration 3. A study of 25 birds found that a positive correlation of 0.53 exists between the weight and the flying speed of the birds. At 1% level of confidence, does there exist a positive correlation between the weight and the flying speed? We will firstly state the null and alternative hypothesis. H naught rho is equal to 0 and HA rho is not equal to 0 and alpha is equal to 0.01. Then we calculate the degree of freedom, that is df is equal to 25 minus 2, which is equal to 23. The critical t values at 1% level of significance are plus minus 2.807. Then we calculate the test statistic T star is approximately equal to 2.997. We reject the null hypothesis at the 1% confidence level. Hence, it confirms that there is a positive and linear relationship between the weight and the flying speed of the birds. Let us now look at the limitations of the correlation coefficient. The first limitation correlation coefficient concept is that it only measures linear relationships between x and y, and for any relationship to exist, any change in x has to have a constant proportional change in y. If the relationship is not linear, then the result is inaccurate. Secondly, if the data is categorically then the relation is meaningless, like the data on hair color or gender. The third, the correlation coefficient does not imply causality, that is, it may show that two variables are strongly correlated, however, it doesn't imply that the variables are responsible for each other. Fourthly, as the formula shows, the calculation of Pearson's R requires the computations of means, deviation scores, and standard deviations, all of which is only meaningful if the variables involved are measured at an interval level. Lastly, Carl Pearson's R is very sensitive to outliers. That is to say, its value can be drastically influenced by a few extreme values. Let us now summarize what we have learned in this module. Association refers to the general relationship between two random variables, while the correlation refers to a more or less a linear relationship between the random variables. Association is a concept, but correlation is a measure of association, and mathematical tools are provided to measure the magnitude of the correlation. Correlation coefficient is a statistical tool to measure the direction and degree, that is closeness, of linear relations between two variables. The correlation coefficient can also take values between -1 through 0 to +1. The sign of the correlation coefficient plus, minus defines the direction of the relationship. The formula R is R equal to sigma xy minus sigma x into sigma y upon n whole upon square root of sigma x square minus sigma x whole square upon n multiplied by sigma y square minus sigma y whole square upon n. When r is equal to 0, it indicates that there is no association between the variables. When r is greater than 0, then it implies a positive association between the variables, that is, the value of one variable increases, so does the value of the other variable. When r is less than 0, it implies a negative association between the variables, that is, as the value of one variable increases, the value of the other variable decreases. The stronger the association of the two variables, the closer the Pearson correlation coefficient R will be to either +1 or -1. We can analyze the existence of a linear relationship by using the t-test for testing the population correlation coefficient. The Pearson's correlation coefficient is associated with certain limitations.